Alright, so I'm going to work another one of these sample problems for you today. It's problem 1270 from the textbook if you're following along. I chose this problem for a couple reasons. One is it may present to you as being something that's a little confusing. I wanted to go through it, just trying to point out some different things along the way. The first thing is it's going to be kind of a concept problem rather than a pure calculation. You might be confused by that, but we're going to have to kind of reason our way through this to come to an answer. But before we talk about the answer, let's talk about the problem. The problem states, which of the following solutions, it gives us three possibilities, it's going to have the highest vapor pressure that results. Okay, so it gives us three solutions. Solution A is one in which 20 grams of glucose with this formula is added to 100 milliliters of the solvent water. The second solution is 20 grams of sucrose. This is actually table sugar. If you have sugar at your house and you add it to your tea or something, here's its formula. You're going to add that to 100 milliliters of water. Okay? And the last possible solution is 10 grams of potassium acetate. Here's its formula. It's a salt. Okay? These are organic molecules. This is an ionic salt. In 100 milliliters of water. Okay, so these are our three possibilities. We want to know which of these solutions will have the highest vapor pressure. Now, whenever I start one of these vapor pressure type problems, I want to remember two things, right? The first thing is that I want to remember that vapor pressures are going to be governed by this Raoult's law relationship, which tells us that P, the vapor pressure exerted by a material in a solution, I call that P solvent. Okay, it's not the vapor pressure of the pure solvent. This is the vapor pressure that the solvent produces over a solution. Okay, when it's dissolved in a solution or a mixture. But that's going to be equal to chi, the mole fraction of that material, whatever that material is. Because remember, it's no longer pure if we make a solution, right? Or make a mixture. And of course, I need to multiply that by P, 0. Where P0 is the vapor pressure of the pure substance. Okay, so I'm going to invoke this law. I may not use it explicitly to do a calculation, but I'm at least going to use it to think about what the answer might be. Now the second thing I need to think about when I'm working these types of problems is what is my mixture? What are the properties of my mixture? Okay, remember I wrote that flow chart up on the whiteboard in lecture the other day. And basically the decision that you had to make was whether or not you have a mixture of 2 or 3 or more compounds which are themselves all volatile. If that's the case, then you add their partial pressures together to get the total pressure, okay? Or do you have the opposite case, where you only have the liquid solvent that exerts a vapor pressure, and whatever is dissolved in the solvent is considered non-volatile? So water, clearly in all our cases, is going to be a volatile solvent, but what about these other materials, okay? Well, I quickly identify glucose, sucrose, and potassium acetate all as being non-volatile solids. They're all generally solids at room temperature. They all are solids at room temperature. They exert very, very low vapor pressures. They're considered non-volatile. So they're not going to play a huge role in establishing a vapor pressure over the mixture. Okay, so these guys aren't going to be important in increasing the vapor pressure, only decreasing the vapor pressure of the water solvent. Okay, so what this question is really asking us is in which of these three solutions will the water have the lowest vapor pressure? And very quickly then, we can come to this equation and try to think about an answer. Okay, because what does this equation tell us? Well, the vapor pressure of the solvent, here that's going to be water, so I might as well just even explicitly state that in my mathematics. Okay, it's going to be equal to the mole fraction of the water times the P0 for water. This is again the vapor pressure for pure water with no solvent dissolved. That's this one over here, okay? Now if I look at this, you might instantly get kind of confused and say, okay, I understand there's this equation, but how am I going to use that here? Because they don't give me the vapor pressure of the pure water. They don't give me the temperature, right? So it seems like I can't use this. I mean, maybe I can compute a mole fraction of water, but I can't use this to solve for pH2O. So I can't figure out, well, that's not really true. because we can rationalize our way through this. Now, I guess the missing link here is that this number, the P0, is the vapor pressure for the pure water. It's going to be the same at the same temperature for all three of these because it's just the vapor pressure of the solvent, the pure solvent that is pure water. It's the same for all three, okay? So that number is the same for all three cases. So then what primarily determines the vapor pressure of all three of these is going to be the mole fraction. This problem basically boils down to figuring out what the mole fraction is for each of the solutions, okay? The solution in which has the highest mole fraction of water will have the highest vapor pressure. So we just got to figure out which of these three has the highest mole fraction of water. Once we do that, we have ourselves an answer. Okay, so what I've done is over on the right, I've actually included some formula weights, molar masses of the three compounds of interest. Now notice we had 20 grams of these, but only 10 grams of this, okay? That could be of consequence. So what we're going to need to actually do here in a first step is figure out the number of moles of each of our solids. So number of moles of glucose will be our first calculation. We know that we're using 20 grams, and its molar mass is 180.15 grams per mole. If we do the math on that, turns out that corresponds to 0.111 mole of glucose. I do a very similar calculation for the sucrose. Number of moles of my table sugar is equal to the 20 grams that's in my solution. It's got a much higher molar mass. It's 342.2965 grams per mole. If I do the math on that, I get mole units back. And it looks like there's 0.0584 moles of that compound. I can do a very, very similar calculation then for the last one. Number of moles of my potassium acetate. Here, I'll write the formula for that one just to save a little bit of space. Now, I only used 10 grams of that here, but the molar mass of potassium acetate is considerably lower. It's only 98.15 grams per mole. As a consequence of that, I'm going to have a little over 0.1 mole of that material dissolved. So I've now successfully completed the calculation how many moles of each material I've got for solutions A through C. Now, you might say, okay, I understand the calculation, but why is that of significance? Well, remember what we want to do is figure out which solution has the highest mole fraction of water, because that's the one that's going to have the highest vapor pressure as well. Now, if I compare solutions A through C, it seems like in each case, don't I have exactly the same quantity of water involved? It's about 100 milliliters. Now I can use the density of 1 because I'm assuming, about room temperature. That would be 100 grams. But I think you could see, regardless of what the value for density is, in each case, at the same temperature, I'm going to have exactly the same amount of water. I'm going to have the same mass of water, at least that can be assumed based on the information given. And therefore, I have the same moles of water in each case. So if I think about my mole fraction calculation to figure out what my mole fraction of water is, I would do number of moles of water divided by my total number of moles of everything. The total number of moles of all components in my mixture. Okay? Now, in the first two cases, right, that would be my number of moles of water plus my number of moles of the sugar, because both of the first two are sugar. Are sugars. Okay? So So I think you can see where we're going with this, or where we're headed with it, right? Because the number of moles of water is the same for all three. Okay, that's not going to change. But what will change is the number of moles of my other component. And if you think about the math just for a second, the bigger this number, the bigger the number of moles of the second component, right? Whatever that second component may be. I might even change that terminology. Instead of take away sugar, just do number of moles of second component, right? But the bigger that is, the smaller the mole fraction of the water. And consequently, that gets smaller, vapor pressure goes down. Okay, so we're basically looking for which of these three solutions has the highest mole fraction of water. Essentially the most concentrated water on a per mole basis, right? And of course, we can figure that out by whichever number of moles is smallest. Right? So as I'm looking at this, it seems pretty clear then that this guy is going to be our winner. The one in the middle, solution B. And of course, the reason why is because it has the smallest number of moles of that secondary component, the smallest number of moles of solute. As a consequence, when we do the math, the mole fraction of that will be the smallest number, and consequently the mole fraction of water will be high, and the vapor pressure will also be highest. Okay, so that's pretty easily rationalized, I think, just by the mathematics. Okay, you don't have to actually do a calculation; you can just rationalize that solution B will have the highest vapor pressure. Now, if I wanted to make this really difficult, I would ask you which one has the lowest vapor pressure. And you might immediately assume that you would look for, well, whichever one of the three has the largest number of moles. And that makes a lot of sense based on what we talked about so far, and you'd probably pick solution A, because it's a little bit bigger than C. But it turns out if you did that, you might be a little disappointed. And this is because of the difference in the molecularity or the molecular nature of the glucose as compared to my potassium acetate down here in the bottom. Okay? Glucose is a molecular solid. When you throw it in water, it will dissolve. It's quite soluble. But it does so to produce one dissolved molecule of glucose. So 1 mole of this produces 1 mole of glucose molecules that are floating around in solution. You have in a solvent, okay? But the thing is, with this potassium acetate, this is an ionic salt. It has a cation, which is K, potassium. It's bad, not a very pretty K, right? But it's meant to be a K for potassium. And it's also got its counterion, which is the acetate, polyatomic anion. It's got a -1 charge. When this one dissolves in water, the ions break up. So 1 mole of this dissolved in water will actually produce 2 moles of particles, 2 moles of different things. One of the moles will be K plus ion, aqueous, floating around. The second will be 1 mole of acetate floating around. So you actually get 2 moles of products for every 1 mole of the stuff that dissolves. Now, what is the consequence of that? Well, it's actually quite important, because if I was to go back to compute my mole fraction for this last one, I need to add my number of moles of all other components in that beaker, in that solution. So I'd actually have 2 terms down here to include instead of 1. I would need number of moles of the K plus ion, and I'd also need number of moles of my acetate, which is the counterion. Okay? So functionally what that would do for me it would kind of like double this number, because this is how many moles of both we would have. So I'd plug that number here for my moles of acetate. I'd also plug that number here for my moles of K+. I'd have to add that to water. So in the mathematics, it would be like doubling this number. And then as a consequence of that, this denominator will become larger than it would for up here. All right, so the mole fraction would be smaller. The mole fraction of water would be smaller in the third case than it would be in the first, even though that wasn't apparent right away. Okay, Now the consequence of that, again, is as the mole fraction of water gets smaller and smaller, the vapor pressure gets smaller. So the third solution would actually have the lowest vapor pressure. But the second one answers our question. What's going to have the highest, because the moles of the second component is lowest. So this is kind of a nice problem. You have to think about using this relationship, not necessarily working calculations. You will see calculation type problems on homework and exams, so don't lose sight of that. But this one was nice because it's very conceptual. You really had to think it through and rationalize things, and that's why it appears in your book. And it's a little bit tricky and a fun one to look at. All right, see you next time.